Hello, dear colleagues. The following presentation depicts some results achieved by a joint team of representatives of Radix LLC, Institute of Cybernetics of the NSS of Ukraine, International Scientific and Technical University, and Poltava State Agrarian University. I would like to share our experience of formal verification methods application to the safety-oriented software development lifecycle. First, I will give a brief introduction of the industry where I work and its specific. I will also quickly show our user application logic lifecycle and the verification procedures that we do. After that, I will show the point of application of formal verification methods and explain our goal. Finally, I will demonstrate a simple example of creating algebraic description of the part of the user application logic, and in the end of my speech, there will be some conclusions about the current achievements and the future expectations. I will try to focus on the main points of the story, so for the other details, you can also check our publication itself. Programmable logic controllers are widely used, and a lot of industrial sectors are using PLCs to automate parts of the process or the process at whole. To achieve higher levels of diversity and dependability, PLCs based on microprocessor hardware and embedded software can work together with PLCs based on FPGA chips. In this case, embedded software is included to the FPGA design. However, PLCs on FPGA have their own disadvantages, like specific design knowledge, specific testing knowledge, quite complicated development and testing tools, and the project compilation takes a lot of time, especially on the big projects. So there could be a compromise, an FPGA-based hardware together with embedded software. An example of such FPGA-based controller is shown on this slide. It's Radix FSC platform. The embedded software, or user application logic as we call it, is developed using Integrated Development Environment, RPCT, abbreviation for Ready Platform Configuration Tool, developed by Radi. It provides much more simple way to define embedded software than the traditional programming approach for the FPGA, more comparable to the microprocessors, I think. And most of the examples shown later are related to the verification of the user application logic developed for this controller. For the critical industries like medical equipment, transportation, power equipment, there is a lot of regulatory documents and standards. And on the slide, there are 3 IEEE standards that are mostly used in my sphere of work. And on the next slide, we can see the software development lifecycle that is often used for the development of user application logic for Radix FSC platform. Most of the elements of this diagram are mostly common to the typical SDLC. However, the specific approach of embedded software has some impact on the development stages. Here we can see the vModel lifecycle and the verification activities that we perform for the typical FSC platform project. As you can see in the table, some of the activities require additional tools developed by Radi, others don't require specific tools and are performed using the standard methods. The diagram displayed on this slide is probably familiar to you. There is a significant increment of resource cost required to fix the bug, depending on the development stage where this bug was detected. Generally, the earlier the bug is detected, the lower is the cost to fix it. Theoretically, by applying as many alternative methods of verification as possible at the earliest stages of product development, we maximize the number of detected defects and minimize the probability of detecting a defect at later stages of the life cycle, when the correction cost increases exponentially. So our main goal is not only to find as much bugs as we can, but to find more bugs at early stages of development. Ideally, the verification methods should be less dependent on the tester skills and experience. So to achieve this, currently we are studying the use of formal verification methods as an additional verification tool in the software lifecycle. Well, to achieve the goal I just mentioned. The formal verification methods in different forms can be applied to the different project artifacts. So we need to first select the point on our life cycle where the application of such methods will be the most efficient. As displayed on the slide, we decided to use formal methods to the UL design stage. Uh, there are several reasons to do that. First of all, this stage is quite early, and therefore the cost of correcting the errors found will be relatively low. At this stage, the representation of most algorithms of user logic goes from abstract formulation by means of functional requirements to the combination of specific basic functional blocks, and therefore they can be formalized with a high degree of accuracy. And finally, unlike the following stages, where part of the verification is performed using software tools, the UL design stage, as can be seen on the slide, is checked by means of technical review and therefore leaves a potential possibility of human error. The use of more automated verification tools and methods at this stage can significantly increase the probability of detecting errors in the design. So let's take a look at the practical example of how it works. I will demonstrate the principles of creating a formalized description of a fragment of the user application logic developed in the RADI platform configuration tool. So the general algorithm consists of three schemas. Each of them contains a combination of elements, like functional elements, input signals, and output signals. I hope the size of the text is readable. And yeah, the first and second algorithms are almost the same. The first one on this slide, and the second is here. They process the input data using discrete and mathematical operations and then transmit the results to the third algorithm. And the third algorithm compares the data from both previous algorithms and sends the results to the output. It's quite simple, but completely enough for the test example. Now let's see what we need to do. I will use the first schema as an example. So first we identify the agents. Agents operate within the schema, exchanging the signals. Each agent function is an element of the schema, and it can receive and transmit a certain number of signals to and from other agents. It is important to separate the agent type and agent instance. For example, both OR element with two inputs have the same type, OR2, but different instances. We also need to define an additional agent, monitoring and tuning station, or MATS. This is the software that provides input data and monitors output data. It is not included to the schema, but since the other agents are operating with the signals affected by MATS, we also need MATS as an agent too, so we adding it here. After all agents on the schema are identified, we proceed into the stage 2. For each agent, we need to define its behavior. For the top level of all three schemas, the behavior will look like the top row. B is the behavior identified, and at the right side of expression, it's the behavioral expression, which is a parallel composition of actions and behaviors. Parallel composition considers various possibilities of sequences of behavior component B. So for the schema S1 ALG, the first schema I showed, the behavior is a parallel composition of P11, P12, and P13, and each of those represents behaviors of schema algorithm parts. Let's check them separately. Here we can see the part of the first schema, two OR elements and a single AND. The result of AND is transmitted to the time filter. The top part is algorithm P11 on the slide, and the P12 describes the bottom part. Its semantic we will check just a few slides later. And finally, the arithmetic part of schema is expression P13. The common thing for all action descriptions is the general syntax. It's instance name, input sources, output destinations, And if necessary, like with example with comparator, it's the additional parameters if necessary. So let's take a closer look at a single agent. Semantic of the actions is the following. The action parameters include an instance list. In the example, S in ACMPC is the instance. S receives signals from instances x1 and x2, could be a signal or a result of another agent, and forwards instances y. Set point real and hysteresis real are other parameters of the element. So the action description starts from a list of local parameters that are necessary for the block operation. The process element of the action can receive signal, like receive x1 signal in, and the process element of the action can send signals like send x2 signal out, signal y. So in this case, instance S sent a signal with the parameter out to instance x2. And the post condition out equals in greater than set point minus hysteresis means that out is set to 1 if in value is bigger than set point minus hysteresis, and otherwise it is 0. And finally, the set of behavior actions for the schema is listed here, the last row. And for the other parts of algorithm, the semantics and description of actions are similar. So that was a relatively short speech about our experience of the application of formal verification method to the safety critical software development lifecycle. So what did we manage to achieve so far? First, the UL lifecycle was adapted through the incorporation of formal verification methods, and the carried out formalization, like we did before, was modeled on an algebraic server and explored for incompleteness and non-determinism. And experimental evidences confirm that the implementation of formal verification methods allow for reduction in testing time and minimize the impact of the tester's expertise level on verification results. So just the goal we were looking to achieve. And what do we do as the perspectives of the described approach? It's the schemas formalization can be automated. Actually, it should be automated, and we're already working on that because now it is processed manually. The developed algebraic models could be used to generate verification tests of binary bitstream code and for the verification of security properties or other specific requirements that may be considered for certain devices. That seems to be everything I was going to tell during this presentation. I hope some of the information was interesting or useful, and if any question remain, feel free to ask unless we are already out of our schedule.
Thank you very much. Dear colleagues, do you have questions? So I have a question. Please, Oleg Hodorushenko. No?
Thank you, Slava. I have one question. How you compared the formalization method you have chosen with other?
Well, thanks for the question. That's quite an interesting one. We didn't do the comparison with other formal verification toolchains or methods yet, because to compare something with something, you need to implement at least one of those. So indeed, there is a lot of other formal verification tool sets. One of the most famous probably is UPPAAL. But with this one, which is the currently used, we had some experience and good recommendations before, so it was easier and hopefully faster to implement this one and to try to implement another one in future just to compare, because the way that we currently working with our user application logic, it can't be just out of the box processed by UPAL, so we will have to adapt it somehow. So the short answer is we didn't made any comparison with the other tools yet, but we will do that as soon as the current approach will be at least implemented at the level that was mentioned in the future perspectives. I hope that answers your question.
Thank you. I think that's a good idea for future research.
Yeah, thanks. We will take it in mind.
Thank you.
Please, Artem.
Okay, thank you. Thank you for your report. And the question about the tools or integrated environment that can be used to perform such kind of formal description of hardware projects. What the tools can be used to simplify this process of formal description?
I will mostly answer relatively to the FSC controller I've mentioned above, because, well, I have most of my experience with it. Since we have the quite strict and constrained semantics for the algebraic server that we are using, we have the user application logic in the form of binary data, like some kind of assembler. We just need to parse that binary file, fetch the calls to the models. Well, we need to define the models, algebraic models for our functional blocks, but we have the limited amount of these blocks, so it can be done. And after that, we can convert. We parse in the binary file. We check in which models should we use. We parse in the method requests and generating similar semantic to the one I demonstrated. The difference is currently we do this manually while we still learn in the semantics and syntax. And at this point, it will be some custom software developed also by us, I think.
Okay, but it's too complicated because part of the task can be done only manually, right? The parsing process and association of the bits and so on.
Well, so it's not exactly. Sorry to interrupt. Not exactly. It is done now manually because well, we just started to work with it, and the models, for one time we need to define the models for all functional blocks that we have. It's like, I don't know, 90, 95, something like this, up to 100. But as soon as we have these models, they are completely the same for different projects that are created for FSC user application logic. So this part will be automated in the future. And actually, the manual work is just to load the binary file to the parser and export the results to the algebraic server. And depending on what are you trying to check, some characteristics of logic, some correctness of model, or maybe generate some test data, work with the results. So in perspective, the whole chain could be automated, but it requires some work in progress.
Okay, thank you.
Dear colleagues, have you another questions? I have question. What do you mean the verification? And do you have validation activity?
Well, we have the validation activity as a part of the life cycle. Maybe I can even quickly find on the life cycle diagram. So we have the validation. I just don't do that. I work on the verification. But we, of course, we have it.
Thank you very much. Are there any other questions? Thank you very much.
Thank you for your attention.
And dear